Okay, so I asked you to sketch a free body diagram for everything you saw in lab on Friday. Well, there are things you're not going to immediately think about, like everybody drew me a ball and a wrap. And pretty much everybody, I think, included hotel. Free body diagram, maybe looks like this. Okay. Where this is friction, that's your normal portion, there's your. And you have examples of that. That's all over your book. Okay. You probably have an example of an Atwood machine, but don't look at the darn thing till you think about it. If you're looking at it, you're just trying to figure out what does that mean? What does that mean? What does that mean? Rather than thinking about the reality. Okay. What happened with that Atwood machine? Now, certainly, at some point, you're going to do, maybe get it in class, maybe you see it in the book, maybe you see it on the web someplace. But don't start there. Start with just trying to figure out what the forces are. You can think about what the forces are. It's not that complicated, but it takes a little practice. Okay. So those are the forces. We've discussed this. Okay. Gravity always acts vertically. Frictional force acts in the direction opposite motion. Normal force acts perpendicular to the incline. Now, if you got an angle down here, you can start labeling angles here, and you can write out the equations for equilibrium. Start with the equations for the sum of the forces, right? And the equation always looks like this. That force equals mass times acceleration. Okay, which means sum of the forces, mass times acceleration. If acceleration is 0, well, we did this last time. That's your equation. It's not sum of fx equals 0, sum of x, fy equals 0, sum of fz equals 0, until you connect this vector equation with those three facts. That's not where you start. You start with the vector equation because it puts you in a context that's going to be useful in all situations. Okay. And of course, the whole sum of fx equals 0, fy equals 0, and so forth is only applicable if you are in equilibrium, and a lot of things aren't in equilibrium, as you probably noticed in lab. Okay. If it was accelerating, it's not in equilibrium. If acceleration is 0, it is. And acceleration can be 0 when something's in motion. Okay, it's not speed up or slowing down. We could set a ball on that ramp and set the ramp just right so that you just barely, your frictional force is equal and opposite to the component of gravity down the incline. Then the ball will roll at constant velocity and it's in equilibrium. Equilibrium means this. That's the only thing equilibrium means. Okay, doesn't mean it's stationary. So make sure you got that firmly in your head. Review what I'm saying here if necessary. Okay, it all goes back to Newton's second law. Yeah, sum of that equals 0. And the sum of all the forces is this. It's not an equilibrium. This is still the sum of the forces, and now you got an acceleration. So you got to think within that framework so that you just have one framework to worry about to apply all these different situations. Okay, so let's talk about the Atwood machine. Everybody did that. Some of these not everybody did. One group got off on finding the magnet repulsion using this balance of some magnets. And then I had them do a simple little thing that we'd already done, but they made it real complicated by getting all kinds of wonderful data. Okay, did a great job on that, using phone accelerometers and stuff like that. And I kind of like to see some of that. Remember, you're supposed to give me your data today. Give you one person, send me their data. So I don't know what we're doing. I don't know what we got to deal with, okay? So now, just as a little lecture here. If this is a engineering group, and I happen to be the supervisor, I'm not gonna be real happy. Because we need to move forward, we don't have what we need to move forward because people didn't get it. Now, at the very least, you could have sent me some data. Said, man, you got too much paperwork this week, I just can't get it. Okay? That makes sense. Then your supervisors can make a judgment and not think that nothing's going on out there. All right. We've got to move forward. We've got assignments because we want to weave this in and out, data reports and analysis. Now, the main analysis I want you to do this week is refine these body diagrams and address everything you saw. For example, one thing I wouldn't have expected anybody to think of it, although I wouldn't have been surprised if somebody had. Okay, what happens when the ball hits the barrier at the end of the ramp? You got a different free body diagram. Okay, so what's that like? And that changes dynamically. Okay, the ball makes its first contact, nothing's compressed all that much, not much force. But pretty quickly, within fractions of a millisecond, the ball's as compressed as it's going to be, and whatever's at the end of the ramp, be it a cup with a metal barrier behind it, which is really cool, or just a plain metal barrier or a wood barrier. What's the nature of that force? How does that force dynamically change? What to think about those things? This gives you insight into a lot of others. Interesting, you have something to look at. We'll talk about this a little bit. That's our miracle polynomial. And I think I mentioned I figured stuff out about this. Started asking myself some questions and realized that this thing doesn't really come off tangent. Okay? Because it accelerates across that magnet radial away from the center and gets a velocity away from the center in addition to its tangential velocity. Let's open an angle more like down here. And if it's moving at 200 centimeters per second, which would correspond to making a complete revolution every second, and it wasn't moving that fast, so it couldn't hit that cup that it did there in the miracle. It changes the analysis a little bit. Yeah, we'll talk about this one. Okay. Let's take the Atwood machine. Now, what I'm really asking for, it's on your assignments page. Posted this yesterday afternoon. I don't expect anybody necessarily look at it, along with problem assignments through next month. Okay? The 18 problems. 12 of them in chapter 5 and 6 of them in chapter 6. There are things that are very closely related to what you see in chapter 5. We'll talk about those on Wednesday. And then the rest of chapter 6 we do next week, and we'll actually be starting chapter 7 because that gets to that deals with energy, and we're going to talk about energy in lab. Get the idea of energy. So we need to make the introduction. We got to catch up a little bit. We lost a week. Okay. And we can't really afford to lose a week. So we've got to catch it up. But we'll do it as gradually as possible. Okay. We also need to have a midterm test for 1st of November. Okay. End of October. So that'll probably be a week after next. We'll talk about it. Okay, now back to this. Here's one of the masses, here's the other mass, right? you know that you automatically have gravity. Not putting the J, I and J's on these things, okay? Generally using J for things that go up and down. But you know, if we change our coordinate system like we do from the ball on the ramp, our coordinate system is going to be like this. It's going to be tilted, so that two of our forces go along the coordinate axis, which simplifies the analysis. If you want to use vertical horizontal coordinate system, go ahead, but it's not going to be happy. Okay. Use a simple coordinate system. Okay, over here, digressing a lot. So let's focus. Let me focus. Okay, here you got it. You got M1GJ. Well, really, free body diagrams are not. You don't draw a picture of the thing. You draw it as a particle. Particle is something that doesn't rotate. Right? The system as a whole rotates. That gets into something we have to address at the multiple level. Okay, so now you've got the gravity force down here. You can go into the detail of this, or just call it negative W1 if you want to. Okay. That'll be a force. This is W2. We call this W1 now. W2, whatever. Okay. So you know that's not the only force because this thing is not accelerating with acceleration of gravity. So what other force could there be? Well, some people think this weight is exerting a force on this weight. No, this weight isn't touching this weight. There's no action at a distance here. Yeah, like this isn't a magnet, and this is a magnet. If it was, then you would have a magnetic attraction, and boy, that would be fun. So that's too complicated. It's more complicated than anything we do in this course. The dynamics of the magnetic field as it changes. If these have magnetic, or one of these is magnetic, and the other just metallic, whatever. Okay. So we don't have any magnetic interaction. There's a gravitational interaction between these things, but it's so tiny that it could be magnetic. Okay. At least not usual proximities. Okay. So we kind of ignore that. What else is there? What is it that's causing this not to fall? Well, it's that doggone thread. It's the tension in the thread. Now, if you take statics, you know, okay, there's tension. Okay? Because you've seen that. If you haven't had statics, well, there's tension. Okay? It's the tension that holds this thing back. And the tension adds focus. Okay? Now, the free body diagram for this one looks exactly the same. Okay, I didn't quite draw it accurately, but let me just make a little change here. One of these has less weight than the other, right? And if you were looking at it from my right, you were looking at it this way, you were seeing this one go down while this one goes up. Okay. Or maybe, no, it's actually probably the opposite. So if you're looking from the opposite direction, you're seeing this will go down while the other goes up. Whatever. Okay. Point is, you're going to have unequal weights. Make sense? So one of these weight vectors is going to be longer than the other. Now, what can you tell me about the tension vector? Well, which one's going up? The way I've drawn these tension vectors. Make this weight vector. Which one's going up? This one or this one? Okay, thumbs up if this one's going up. Yeah, because you got more tension than you got weight. That's why it goes up. Okay, what about this one? Up or down? Well, you know it's going down. Why? Because the width is greater than the tension. Now, thing you need to know about this situation, because this free body diagram is real simple. You got to know a little bit more about what's going on. Okay. You know there's got to be something that's keeping this from falling, and something's keeping this from falling through. Okay. The other thing is, we can really say we got a tension T1 and a tension T2. Except I just use one because if you have low friction, I said low friction, I'm going to say negligible friction. And T1 equals T2. There's nothing between this end of the string and this end of the string to cause any reduction in tension. Okay, now if you have friction, then between here and the pulley, okay, you've got one tension. Between the pulley and the other mass, you've got another tension. And the difference in the tensions is the frictional force. So hopefully that halfway makes sense. But right now, we're not going to worry about frictional forces. We're just going to say friction is negligible so that this string is just stretched exactly the same way, strained exactly the same way on one side as the other. Okay, stretched out as much. That makes sense? And those frictions are very low pulley. Somebody noticed that when the thing slipped off, the pulley kept going for hours. Well, not really hours, but a couple of minutes. Okay, very low friction. That's why they cause $40, something like that. Well engineered, impressed. Okay. Now you probably want to know that much about the application. That's kind of okay. Well, I've gone too far afield. Once we had a situation like this, you can see this and you both have problems. So what if you got a mass here? And a mass here. Low friction pull. What do the forces here look like? They look exactly like the forces here. It's just the same as mass that's coming down, right? Actually, look at this. This mass is going to descend unless friction holds it back. Okay. Over here, you got mass M1. So let's see, you got M1. You got M1 G, right? Multiply that J, put a negative, you know, you got the net. Okay, you got the normal force. You got a tension. And the tension here is the same as tension here. And you got a friction force. Okay. Now, if you got enough friction, that frictional force will be bigger. Okay. Right now, your coefficient of friction is just the ratio of the length of this vector to the length of this vector. What's that ratio? What? Is this 0.5 of this? Well, 0.5 of that would be half, it would be that long, and it's not nearly that long. What? Show me with your finger. Five? No. Which fingers? Okay, that's okay. Okay, you think it's 0.1. What do the rest of you think? 0.2, 0.1, 0.2, 0.1. 0.2 or 0.3. There it is. How many of these it take to make this? 1, 2, 3 doesn't quite do it, but that would make it 1/3. I think it's closer to 0.3 than 0.2. I think 0.1 is a little low, but that's okay. Do you see that? And 10 of these would be longer than this. Okay. 5 of these, I think, would be longer than this. 3 of them might be a little shorter. So somewhere between 0.2 and 0.3. Maybe around 0.3, maybe 0.28. You know. Okay, does that help? That gives you a little insight. You know, look back at this video. It's not hard to find where it was this diagram I'm talking about. Okay. And then, of course, over here you got M2. So now you got M2G. Guess I better go a little longer than that. Tension's over the top. And tension. Tension's equal to this tension. Put the tag on it, but I just put the R over 2, 1, and T2 there to cover it. You don't always need to do that. Okay. Well, at this point, if you've got information about the coefficient of friction and the masses, you've got equations you can write to tell you what the motion of this thing's going to be. So we'd start with a free body diagram, start with the picture. Okay. I'm not going to talk about all the situations because I want you to think through them. Okay. Let's just have you think about a pendulum. Okay, now if it's a pendulum away from equilibrium, and you got the weight, I'll just use W for the weight, but you could do MV times the J vector if you want, and that might be fine. But there's a weight, right? And then I was holding it back, so I was probably exerting the force. Let's just assume my force was horizontal. I mean, it could have been pushing it up and back, right? Okay. But let's assume that it was a horizontal force. And that kind of depends on where my finger contacts the pendulum, also the shape of my finger. If my finger is contacting this pendulum ball real low, then it's certainly giving it a force. It's basically normal to the surface. It is normal to the surface. So if the point of contact is out here, it's put along the horizontal axis through the center, then tangent to that, or the normal to that, is going to be this way. And okay, don't want to say too much about that. And then the tension's not straight up. Some people wanted to draw it straight up. Tension is in that string. That string trying to get shorter. If that string gets shorter, what direction does this thing have to go? It has to go this way. Your free body diagram is just this, or maybe this, where this isn't necessarily assumed to be a right angle. Okay. Here's a question about direction of that point. Taking the simplest assumption that it's horizontal, there's your picture. And that's the picture we're going to want to use for this. Okay. Now, what if you take my finger away? What's your free body diagram look like? Remove my finger at that instant. As soon as my finger loses contact and the pendulum ball then it's just vibrating from the compression, which is so small you can't even detect it. What happens? Okay, now there's a strong tendency to invoke fictitious forces from our intuition. Okay, and a couple of people did this. For the pendulum, if this isn't here, then this isn't here. And there's your free body diagram. Some people wanted to put a vector in this direction, and there's no such thing. Okay, there's nothing forcing it in that direction except the horizontal component of the tension, and it's already there. You don't have to draw it again. Have double the acceleration of the pendulum and ruin the universe. You don't want to ruin the universe, okay? Seriously, seriously, we don't want to ruin the universe. We're trying awful hard. Don't think we have to follow it. Okay, so that makes sense. That's it. Now you can take this tension here and you remove it and replace it by its components. Well, kind of missed my hand was in the way of my card. Okay. Well, but you understand what I'm doing? I can take any vector and draw a little wiggly line through it to make it go away and reappear as two components. It's two vectors, right? Totally equivalent. This vector is totally equivalent to these. With the pendulum, for small displacement from equilibrium, the motion is going to be nearly horizontal. I just had that pendulum about, 4 feet long, pulled back about a few centimeters, right? Now it's going to follow the arc of the circle, but it's going to be a circle with pretty big radius. And through that few centimeters, it's going to be almost a straight line. Well, you make that assumption. And if that assumption is true, then, well, the vertical component is pretty much equal to the magnitude of the tension because this is a small angle. Cosine of a small angle is close to 1. Yeah, I'm just kind of throwing out some ideas for you to think about. The sine of this angle is going to give you this component, and that's what accelerates the pendulum back toward equilibrium. Now you get on the other side of equilibrium, and it's accelerated back this way because the tension is going to be in this direction. Make sense? So again, you want to get used to doing free body diagrams. That's an important one. Matter of fact, simple harmonic motion, which is what comes out of this, is probably the most important type of motion we study. Another comment, people keep wanting to use the equations of uniformly accelerated motion. And it's a bad mistake. Okay, I beat that out of last year's class finally. First time in almost 53 years. I had a class, nobody trying to do that on the exam. We'll talk about that later. But obviously, as this angle changes, as the angle of the pendulum changes, the angle of the tension changes, right? So this component changes, so the force changes. So the acceleration changes, and it's not uniform acceleration, right? And that's why we want to look at the dynamics of some of these situations, okay? And in the way I've stated the problems in the assignment. Okay, well, let's see. I'm not sure I even want to talk about the penny at this point. I'll probably save that till next time because it's a little bit conceptually difficult and complicated. There's nothing really conceptually difficult about these things once you get used to it. Until you get into really complicated situations. There's one I read in a physics journal. Here's the American Association of Physics Teachers. I think my old advisor and colleague was dean at Cal Poly and also might have been the head editor, he might have been the president of the association. Really good guy. Hated it when he left. Okay. But he kind of got kicked out. He's on a postdoc or something. Everybody was a good guy. Anyhow, that term. Okay. You got a disc with a rocket engine on the rim. And you fire that rocket engine. Analyze the motion of that disc. Most PhD physicists are unable to do that. Okay. It's really tricky. Matter of fact, I think I understood it when I read it. I don't think I understand it. Sometime when I'm up late at night, maybe get back to sleep, that one might be a good one to put me back to sleep. Try to analyze that. I think you probably want to go to generalized coordinates and all that. So you don't want to go with that. Okay, not in this course, not at this level, probably not ever. All right. Okay, back to examples. Okay, simple example is you got this kitchen balance, you got a magnet here, you turn the thing on and it shows you nothing because I'm moving at zero net force, right? Now I've got this magnet out here. And already when I do that, I'm getting 6 grams, which is not a unit of force, but 6 grams times the acceleration of gravity of force, right? And I move it closer and force decreases. Okay. Now there's something weird about that. This goes negative now. Okay, well, so it must be a force of repulsion. How did I get 7 grams there? It's terrible. And that's a force, it's got to be a force of attraction. Yeah, it's a force of attraction. I'm being ignorant. Okay, right now it reached 3 grams, now it's 2 grams. Okay. Now it's 0 grams. Somehow there's negative, now it's negative. That's got to be a force of repulsion because of the way it moves. Anyhow, you figure that out. You draw the free body diagram and you can answer all those questions. Okay. And then in the situation that you're familiar with, because we've done it, you space, we use domino spacing. We're going to do a diagram and then we're going to talk about the free body diagram. But you can use a stack of dominoes to space this with another domino or with another magnet, right? And release it, it'll accelerate. And if you're on the part of a tabletop that goes a little bit uphill, it'll eventually come to rest if your magnets aren't too powerful or if you're not too close. So there are all kinds of things to think about. Now you know what the situation is. Everybody's had their hands in this thing with magnets, right? Or slab. Okay. So this free body diagram, it's the instant of release. Compare with a free body diagram half a second later. Draw me a free body diagram for that cart at the instant of release, just after it's been released. If you got a second after class, holler at me. Okay. Otherwise, I'll email it. Okay. We have the cart with the magnets and the situation. Like, here's your cards, stuff. And here's a stack of dominoes. And here's the magnet. Spacers, magnet, and there's a magnet on the end of the card. Now, before you release it, well, you got the force exerted by your finger And if you're holding it down by pushing down on it, that increases the normal force, right? Okay, but if you're pushing back this way, yeah, it could be any number of things. You should be able to do a free body diagram for that. And at the instant, just after release, you have some a lot of people use repulsion, that's fine. But there's the force of the magnet, right? There's a magnetic force. You have negative mgj here. And you have the normal force here. You got the force of friction here. Okay. Now, very quickly, sketch it and circle it so I can see it quickly. Do the same diagram when the thing's 10 centimeters away. About that far away. What's it going to look like? Okay, so after this thing's moved 10 centimeters, the magnetic force, you know, is going to drop off. Pretty distracting. Pretty drastically. Okay. So you're going to have much less force in the magnet. Still got friction. And you got your weight and your normal force. Now your weight and your normal force, in this case, are going to be equal and opposite because the thing is not accelerating up off the table or down into the table. It's staying in equilibrium with respect to the y direction, if you will. Okay, I didn't quite get this vector long enough. These two should be equal and opposites. Stand that point out to where okay, so basically the frictional force gets a lot closer to the magnetic force. Frictional force doesn't change. It was rolling here, it's rolling here. And your rolling friction we assume to be constant. Because it's the same wheels. Now, eventually, a long time later, what's it look like? Well, you got your normal force, weight, your frictional force, and almost no magnetic force, right? And of course, this is why it comes to rest. That's going to be important next week, especially toward the end of the week, when we talk about energy. The energy to get out of the magnet. When this thing stops speeding up, and these forces are equal and opposite, right? Because then your acceleration is zero. All the forces are in balance, one instant. Okay, then it starts slowing down, and the whole velocity profile, which you can get with an accelerometer, okay, very quickly, it's very easy to get it. So if you don't have that, you get it again, and everybody can. Anybody's got an accelerometer. Okay, very good. Hopefully, it gives you enough to think about that you can do the assignment to do all kinds of interesting free body diagrams. I'm trying to think of some that I haven't